Hello, can everybody hear me? Great. Okay, today I'm going to be talking about voting machine technology. My name is Tom Trumpor. I'm a consultant in the United States. I live in the New York metro area in the state of Connecticut. So anyway, let's start here. Okay. First, what we're going to do is go into the history of voting machines, and we'll start with uniform paper ballots. And we have first, with uniform paper ballots, voters make choices in private. They mark boxes, and then they drop the ballot into a sealed box. So it's basically a pre-printed form that was first done in 1856 in Victoria, Australia was the first place it was done. So, and by the way, a lot of the things I'm going to talk about are going to be things about the United States, and I talk about it not because I think we do things better there or anything, it's just the perspective I come from. So, but anyway, the Australians, they're pretty cutting edge on a lot of things actually, and they're doing a lot with DRE, with electronic voting, as we even speak. So anyway, so they started that in 1856, and in the US we began using them in New York in 1889. And currently they're used in less than 2% of all the voting in the United States. So anyway, yeah, very very few. They are used, in mostly rural areas. They were used in Florida, I know, in the 2000 election, the very controversial 2000 election in Union County. Okay, so the next thing was mechanical lever machines. And what it is a lever closes a privacy curtain, which then initializes the machine. And then what happens is the voter then goes ahead and makes their vote. And when the vote is actually finalized, there's little dials that go 1/10 of a rotation each, or 36 degrees. So it goes 36 degrees, and then it turns the next digit and the next digit. And then, so that's how that works. They were first used in Lockport, New York for the first time in 1892. And every major U.S. city, every major U.S. city in the 1930s had them. And then by the 1960s, we had, at least half of the U.S. wound up having these machines, but now they're down to 20%, and they keep dwindling. They get replaced by mostly DRE technology. All right, so the next iteration here is punch cards, and voters punch holes in cards and into cards which are put into ballot boxes, and they're later computer tabulated at the precinct. And they were first used, I put Georgia here, Georgia, the United States, in 1964. And there are two types. There's the vote-matic, which numbers correspond to each person that you actually vote for. And then there's the data vote. And what data vote is there's names next to the holes. There's like a booklet. And as you turn each page, a new row of chads that you can punch out are exposed. And then you hit each one, punch each one out as you turn each page. And that's how that one works. And by 1996, they were used by 37% of the U.S. So anyway, a lot of this information, they spoke about it in an MIT report, but I actually had to fill some gaps because they came short on a lot of the history. So if it seems somewhat spotty, it's just that there was a lot that they didn't have. That I actually got a report sent to the United States Congress by a man named Fisher, and that seemed to fill in some of the holes that the MIT people didn't have. Anyway, optical scan is the next. And they're a lot like taking a test with a number 2 pencil where you fill in the hole, and then you go ahead and it gets read by a machine, which later it gets tabulated at the precinct and then sent up. They began use in the early 1980s. The exact origin is unknown. I know they were used in the 1980 general election in California, and they had quite a lot of problems at that time. So that's the earliest we know. We know at least in November of 1980 they were used. So anyway, they're used by 24% of the U.S. By the late 1990s, and I'm sure they're going down also due to the standard electronic touch screens. Okay, and then the next we're going to talk about DRE, and like lever machines, most of them do not have any kind of paper at all, and the user touches the screen or pushes buttons that they touch. It's touching a screen if it's deballed. If it's Sequoia, then there's these buttons that you would press, and the results are either stored to memory disk, and in some cases it's in smart card, and you can't get much on a smart card, so all you're really going to get there are just the end results. And they began use sometime in the 1970s. Although we consider it the latest thing because, they've come an awful long way since then as far as, back then, how much could you really do? You couldn't really do touch screen or a lot of things. They didn't even have mice back then. So by the late 90s, they were used by 8%, but according to IEEE, they're now over 25% now. And the bulk of this talk is going to concentrate on DREs. All right, here's some reliability statistics. These statistics were done, it's part of that report by Caltech, MIT. And what these are averaged in statistics. They had a lot of different statistics. And generally what their conclusions were, if you look at all their statistics, is that optical scanned and lever machines and paper ballots, those three, always did better than punch card and DRE. That's generally how it came out. And let's see, if we look at, for example, lever machines, they're number 2 in the average statistics. But what happens is sometimes it jumps above optical scan and back and forth, or even below paper ballots at times. It will do that. And that one can get really high when it's not a presidential election. For some reason, when you have like a senatorial, gubernatorial type of voting system, the residual goes higher. Now, Caltech MIT defines residual as being a situation where you cannot tell who the president, whoever they're voting for, is. You can't tell. It's, somebody didn't fill out both. And their conclusions overall were that basically they think that it's people getting acquainted with the equipment was their thought on it. Their study in no way talked about any of the vulnerabilities. They just looked at, what situations you couldn't tell who voted for who. So anyway, but let's talk real briefly about some of the vulnerabilities of each of these technologies. Optical scan, for example, what would be a vulnerability? Well, they do get computer tabulated, and so if there's something you could do with those computer results in the end, that would be a vulnerability. And I'm actually surprised that overall they seem so reliable, because you would think that something would happen there, because there's been so much that have happened with DREs along the way. But then lever machines, a way to fix that would be to maybe file down or break off part of the teeth in the gears. So you would do that to the opponent, somebody that you didn't want, and then the gears would never move. So that would be one way to do that. Paper ballots, stuffing the voting box would be one way there. Maybe trying to do something along the chain of custody when the box moves around. That would be a way to do that. Punch cards, there's two ways you could cheat there. One would be is if you just poke a hole, you get a whole stack of them, and you take a big rod and just poke a hole through the person you want to win. So now you have a situation where it looks like, the person you want to win, all of a sudden, their chads are already out, so it's okay. But now you got double voting in situations where somebody voted for someone else, and then you just throw that out as, being residual because, oh, well, this guy couldn't decide who he wanted both of them. So that would be a way to cheat there. And another would be to put an adhesive in the back of it, where when somebody goes and pokes a hole, it would pretty much snap the chad back and it would keep it there. So those would be two ways there. And DRE, well, we'll talk quite a bit about all the problems that can happen there. All right, we'll talk about the Dball Code here. The code I'm going to talk about is for the client system, which was first discovered on Dball's FTP site in January of 2003. And while officials seemed very unconcerned and very nonchalant about what had happened with the, with it being out there. They really they took the code off the minute they discovered it, which was very late January of 2003. They finally took that public code down, and Dball has not taken any action about mirror code available publicly. They have taken action. There's been a bunch of memos that have gone around that basically, they were internal memos that said, yeah, we know we've got a lot of problems with this technology and things are not working right. And people have put that out on their websites. And people who have done that have gotten cease and desist orders for that. But for the code itself, they hadn't taken any action about that, about the source code. So anyway, let's go over the code here. The code is for the terminal voting system, AccuVote TS terminal server, and not the GEMS backend management system, which does the final tallying in a remote area. The code was written in C++, which could be a problem because if it's not in tight control, as a lot of us know, you can have buffer overflow problems, which you would not have, say, with C# or Java. And the terminals are configured under multiple Microsoft environments. The only environment I haven't seen it is an XP, but it's predominantly used with Windows CE. So let's see, and the design summary here is the way they meant it to be is a ballot gets configured, and stored to a file. That file is called election EDB. Echo David Bravo, election EDB. And let's see, what happens is it's either stored to a removable media, or they can get it remotely via, modem, dial-up, or the internet. And then when the system is initialized, the voters go ahead and they vote with these special smart cards that are to be reset after voting. And then an ender or administrator card at the very end gives the okay to send all the votes to be tallied at the GEM system at the end. Okay, the vulnerabilities here. We got CE. The first thing is, what they did is they had it where you would have a separate drive, be it a USB, some kind of separate kind of hardware, and that redundancy was there so that if something went wrong, you would if the disk crashed or whatever, you would still have those results. Well, a vulnerability is you just take the card out, you basically mount a new, create a new directory, and there's no double checking whatsoever. Like in Unix, you could do a DF or something to check, and I'm not saying that in Microsoft you couldn't do it. It's pretty simple, in other systems to quickly look, but these guys completely overlook that idea of making sure that the drive is really there. And then one can program smart cards for multiple voters, and then there's the administrative functions as well. So anyway, here's the thing about smart cards. They're unencrypted. There's no encryption whatsoever. So somebody could just go in, if they know the fields, if they can figure things out. They basically use the ISO 7816 standard. So, if you know all that, and there's plenty of places on the internet where you can just buy smart cards. Some of them as cheap as like 10 for $100, and you could get. So one way you could cheat the system is you could make a whole bunch of voter smart cards. But the really clever adversary, what they would do is to get a smart card, and the way the bits are set, the bits, number 1 is a voter card, number 2 is an ender card, number 4 is the administrator card, and then number 8, so you could see they use each bit, and number 8 means that the card is invalid and it's been used. So anyway, what the clever adversary would do is they would take the actual, when it says, okay, turn this 1 bit to an 8 after voting, they would just say, okay, go ahead and make it a 1 again. And you can keep voting and voting and voting with the same card. So it's quite a problem there. And then, administrative functions, they're again, I told you how that works. Passwords and that kind of thing, they're stored on the card, unencrypted, and then there's, a lot of issues there. Well, I'll get into it later because there's more on that. Encryption is not used or used properly, and reporting to the GEMS, in this case, does not use any encryption. Now, I did read some IEEE report that said that this has actually been done, but the scary thing is they give you an option whether you want to send your information encrypted or not. And that kind of tells me, when that option is there and they just don't force it to go out encrypted, that there's probably still problems with the way it communicates. And so, it's kind of a fail back if they need that kind of thing. Okay, let's see. Phone lines, internet, wireless are all ways for man-in-the-middle attacks. You know, if you're at an ISP or something like that, and you're in the middle, you could, since everything is sent unencrypted, all that data, somebody in the middle could just grab it, massage it the way they want. They could even do a little math to make sure that the number of voters are correct on each side, and then boom, ship it off. So that's one vulnerability there. And so anyway, there's no change control process to prevent coders from adding any kind of malicious code. And I could see how this would happen, because obviously, you know, with the Help America Vote Act, what happened is after 2000 and that whole Florida debacle, what happened was, you know, they wanted things solved very quickly, and the big fix was going to be DRE machines, and so basically it was like, let's get this done now, let's hurry up, and a lot of federal funds were thrown at these companies, and just hurry it up, let's just get it done. And so you could see, you know, to get things done very quickly, you wouldn't want that as a hurdle. There are two methods for DOS attacks. One is the admin or ender card, and the other is ballot definitions from a remote site. So basically, in the admin or ender card, what you could do is you could actually, let's say, pick a time to just end it, you know, and you could pick, say, lunchtime when it's really busy, and you could just copy these, make these ender cards pretty easily, and just stop the election right there, and that would be one way. And then the definitions from the remote site. This one's a bit of a stretch, but you know, it could happen. You know, you could have a situation where the poll workers don't set the definition files till the very last second, and so what would happen is at the last second, they would try to go through the internet, or they would try to go through a modem, and if somebody somehow, you know, did a DOS attack on the internet, or just clipped the phone line, you'd have quite a problem, and it would probably be hours before you could get things going again. So anyway, PIN numbers are stored, again, unprotected on the card, and they're just in the clear. And the funny thing is when you do the challenge, and the pins are only used for the administrator card, they're not for the ender card. So what happens is you know, when you go and put the card in, well, it's sent also plain text from the card reader to the terminal. So there's another vulnerability, because it's out in the clear, so somebody looking at the traffic could get it that way, or if somebody had access to a card, they could do it. But even another adversary, without even knowing what the PIN is, could put a PIN on the card, and then when it sends it, you know, they would know what to type, you know, because they pre-programmed it. So it's, you know, it's, I think the people that put this together, they thought, well, smart card, you know, and they didn't think, well, wait a minute, there's a lot that goes into implementation when you do a smart card. So, you know, it's pretty rough that way. The password and encrypted keys are hard-coded in the source, and they're sent plain text, you know, to and from things, and so there's a whole lot of vulnerability there, because it's in the code itself, it's on the card, and it's also being sent back and forth plain text. And you know, the other thing is that we'll go over this in a moment, but also there's a failback about whether you know, to go to the actual there's a failback where you would go and go to the manufacturer's default password if you don't know what to do. So yeah, that's what we're talking about here. The manufacturer, whatever default password, if somebody can't get the one, well, you can just do that, and then you're okay. So there's 2 passwords. So the manufacturer's default, that's not very secure. Configuration is done in the clear within the registry. It's done in Microsoft, so they have it in the registry. There's no encryption to anything in the registry. It's just out there in the open. So, if you know about Microsoft and can just run regedit and look over things, boom, you can get in an awful lot in there. So anyway, we were saying, the terminal and the terminal serial and the COM ports are in there. Candidate order on the ballot matters. So here's another way you could fake the system out. If you take, let's say you're dealing with and a lot of these kinds of attacks are areas that you would know that this precinct goes a certain way. It goes mostly Republican, it goes mostly Democrat. And so what you could do is reverse the order of how things appear, and then when GEMS goes to tally it, it would go to your advantage if if you didn't want that certain candidate. So the database is in Microsoft Access, which we know is not a very robust one compared to SQL Server is a little more robust, and then something like Oracle or Sybase, which is a lot more heavy duty with triggers and stored procedures and things that you can do to really lock down the system. And also those databases, you can have many more records, which is a problem. I know there was one vendor, Unilect, out of Dublin, California, and these guys, they had a problem in North Carolina in one county where they told them, yeah, this thing will handle at least 10,000 votes, and in reality it could only handle like 3,005. And so, close to 4,000 votes wound up getting thrown out because, they just stopped tabulating after a while. So this is a big problem when you use these homemade type databases or things that are just, don't have a lot of capacity. And then database design lacks referential integrity. So in other words, instead of sequentially going, okay, here's a record, and it does things sequentially anyway, so it's not like it's trying to do things random to give people anonymity when they vote. Because that's, that's one of the things you're trying to do, is give people anonymity so that, there can't be any kind of threat that would come back to them, or people couldn't be bought off somehow. And so, there's nothing like that. Things are done sequentially, but there's no, like, taking a hard key, like taking a key that would be a primary key that would be numbered sequentially, so you could say, this record must have been deleted because it's, there's a gap between these numbers, or there are a few records deleted. There's nothing like that going on. So let's go over some of the code here, and here's a code sample. We've got basically, let's look here. We've got, this is the situation where the passwords are actually on the cards themselves. And as you can see, it says select file, and that 0x3d40, that's basically, that number there is how the files are stored. They're actually stored as a number on a smart card. It's not a file name on the smart card, it's a number. But as you can see, it first tries and it sees if it's the EDOA, etc. And if it doesn't do that, then you can see that it tries to do it. It just says, well, just grab the manufacturer and just, go from there and change it back and just work with the manufacturer and that kind of thing. So there's something real obvious there. All right. Okay, here the encryption key, as you can see. And when I saw this number at first, I thought, well, it's hex, but it's actually a character because that H in there, it's just a standard, in the clear kind of thing. And so that the key is to do the encryption is actually done, where there's no kind of key management. It's just in the code itself, and you can get at it that way. And so that's quite the problem. Is and the other thing is that basically there's a checksum, and that checksum is stored in the clear. So if you do crypto analysis, there's another thing that you can do, since in the files, it's sitting out there in the open. And here, it does it in CBC encryption mode, not to be confused with CRC, although they use a CRC, but they go ahead, and then if you see there's a null here, and this null is a problem because in this function, what you want to do is you want to use as random numbers as possible. And when you put null, it just automatically goes to 0. So when this function is done, it's just done with 0 every time. And so when the encryption is done, it's just, like I said, somebody who does crypto analysis, they know that this function is done with a 0 rather than a random number. They would have been better off if they had just used the computer's internal random number generator that doesn't depend on any kind of behavior. Even that would have been better, even though most crypto analysts say that's not even a great way to go, but that would have been far better than to just use 0 every time. So, all right. So here's some comments, and the comments can get kind of scary in places. So here's the first one. It says, parse the file until the EOF token. If we get too many errors at this level, we abort. So what constitutes too many errors? I mean, what's the arbitrary number here? That's kind of a scary thing. And then in this one, they talk about the character length. And the guy's asking, why the magic number 9? And what I noticed about this code is in most places where they have these triple X's, it usually gets pretty interesting, And it usually gets to be something else. Here's another one. Okay, I don't like this one bit. It's really tough to tell where, and it goes on and on. Now, this one was actually published in a report that was done by Johns Hopkins Rice University. A bunch of computer scientists analyzed this code much the way I'm talking to you about it. And what they did is they published this, but they didn't publish it. They took out the part now. They say the solution chosen is, and so they weren't. I'm being a little more fair here. At least they're attempting they're using the term solution. And in their situation, they write the beginning of this, then they go ... and it says a reorganization might be in order here. So anyway, they're not as fair. They did some checking on the backgrounds of the people that did this, and most of them are legit. They said one person looked like they had a conflict of interest, but most of the computer scientists that looked at the code and were doing things had no real axe to grind. They were pretty legit. And then as you see here at the very bottom, you can see there's a bracket here. So this is the beginning of an actual function, and then they put a comment in the beginning of that function that's going, and they just put error, error, error. And I found a couple of those in the code when I was scanning through it. It was something else. Okay, here's some web resources, and then we'll have some time for questions. But the web resources, if you want to play with the code, this is the place to go. You can get the code here at countthevote.org, and it's in a CVS tar format. If you were to look, if for some reason this goes away, because I don't know, I found this code every now and then, it just will leave a site and it goes somewhere else and it goes from place to place. If you're looking on a search engine, what I would do is I would search on CVS tar, and I would, in Google or something, and then just do put Dball and put -Linux, because there's like CVS tar. That's a totally different thing for Linux. So that's how you would search for that. Anyway, the next one is blackboxvoting.org. That's Bev Harris's site, and you can download her book. It's in PDF format, and she talks about all kinds of vulnerabilities and problems that voting machines have. And then we go next to the Electronic Frontiers Foundation.org. And you could just go to their home site and click on e-voting, but there's so much. This site has so much to do with electronic media and freedoms. And this is just one aspect. The e-voting is just one aspect of the whole site. So if you want to go direct, you can just go to that activism e-voting site. And that's a pretty good one to go to, where they have a lot of different references and things. And then the next is Wired in the news e-vote area. Wired is really, I mean, the name of the magazine sounds like they're really going to get into the nuts and bolts of the thing and really clamp down and let you know what goes on. But it's really more, it's not really like that. Wired is more just informational, and things about technology where just about anybody without a technical background could read it. But it's pretty good, this site, because you can see a lot of the stories of what goes on, and the different DRE machines. Like their most recent story is about a vendor in Ohio that just went ahead and did a bunch of resetting, and one of the congressmen, John Conyers, is instructing the FBI to look into why was this done. When you're trying to investigate what's happening, why was something reset and a new patch put out there for people to look at. And out of all of these, if there's any two that I would look at, out of all of those, I would go Black Box and Electronic Frontiers Foundation. Because if you go to EFF, you can get to countthevote.org and that kind of thing. And so anyway, that's pretty much that. Are there any kind of questions out there? Yeah.
Now, okay. Now you have made it absolutely clear, and especially to this crowd, that this voting machine system is not fit for a trustworthy electronic voting. My question to you is, you have found this very early on, and so what do you think? Why was the American system not capable of taking your real concerns into account and come up with a better voting system?
Yeah, I think what happened in that situation is, there was just a lot of corporate things going on. And, you know, in the United States, we obviously have, you know, a situation that's very pro-commerce because we have, you know, an awful lot of Republican things going on right now. You've got a House and Senate that's predominantly Republican. You've got a justice system that tends to vote very conservatively when it comes to justice issues, and then the presidency itself. So, and I just think, you know, a lot of these corporations overall, just the media didn't really cover this. They really didn't. In fact, for the most part, when articles came out in the media about electronic voting systems, instead of getting into the nuts and bolts like this, you know, it's not that, you know, I mean, don't get me wrong, a lot of Americans are not very knowledgeable, but it's not that they're all entirely stupid. If they're just given all the wrong information or very little information, how can they really make informed decisions? So the media, when it comes time to actually report, they just talk about how fun it is and how easy these machines are to operate. And if you look, you know, if you look at one of these machines, like the Dball one, it looks nice. I mean, it looks like a really slick, well put together, a lot of symmetry, and you look at the machine and it looks like, wow, but you know, when you actually open it up and look at it, you know, there's a lot of problems. Now, this code is going to be close to 2 years old because it's 2 years old basically because, you know, they discovered it in January 2003, and there have been some fixes along the way. Like I said, I know that they have it where you can now encrypt when you transmit. So, you know, who knows what kinds of fixes that they've made since then, because nobody's gotten at the source since that time. And, but a good clue is that they did publish a bunch of code, and it's not necessarily source, but they did publish something that could be reverse compiled or looked at. They did publish something for the GEMS system on the internet as recently as a little more than a month ago. So that's going to give a lot of clues as to how much they've really fixed and got together. But yeah, I just think there's just too many vested interests right now, and that's why, you know, I mean, one of the voting systems, it's like, is run by a congressman, a Republican congressman in the United States. So, you know, that's just, unfortunately, you know, you have a situation like that, a conflict of interest like that. It's, you know, they're going to keep all this stuff as hush-hush as they possibly can. And by the way, the Sequoia code, there's Sequoia code out there on the net too, if you go to look for that. And you can look at, and Sequoia certainly has vulnerabilities too. They're all not alone. So, okay, next question.
Okay. I'm a researcher in software requirements specification and verification, and I certainly know what it takes to make verified and correct and reliable code. And having seen the examples, I very much doubt that they can just patch it up to make it reliable. And the other thing is, even if they would start from scratch and make good specifications and verify the requirement specifications and work from that with formal and proved methods, there still has to be the trust in the public, in the machines. And if there is sufficient mistrust in voting machines, in DRE machines, then it doesn't really matter if it's really reliable, because if people don't trust it, it's not any good. And the only thing to restore trust in voting when using DRE machines is to produce what's called a voter-verified paper ballot. That is, you vote on the touch screen, and when you say, yes, this is the vote that I want to vote, it produces an actual slip of paper which has your vote printed on it. And you put that in a ballot box, just like with a paper ballot. And if anyone challenges the election in that precinct, you can take the voter verified, the actual correct paper ballots, and recount them by hand. So you don't have to rely on the electronic systems. And are there machines like that to come in the United States that produce every time someone votes on a DRE machine a voter-verified paper ballot.
Yeah, there's been some of that, but in most situations, most of the time, it's just thrown in the bit bucket, and that's the end of it, unfortunately. Paper would be wonderful. I know Bev Harris is a big proponent of paper, but
that's of course the one advantage that the optically scanned paper ballots have, because you still have a paper ballot that, if need be, can be counted by hand.
right. There's one scary thing, though, believe it or not. Even though optical scanning, you can go back to that paper, there are actually laws, and is it laziness? Is it to save on labor costs? What is it? But where there's some laws in some situations where you're not allowed to go back and count those, believe it or not, in the United States. It goes that far, if you can believe. Yeah, it doesn't seem very smart, but there are some laws that say, oh, you can't go back and do that, which is just outright ridiculous.
Yeah, but it comes down whether or not you can trust the black box that is the voting machine, or just the counting machine behind the optical scanner.
Yeah,
but usually you can't.
Yeah, but optical scanners are great for that reason. I'm actually surprised that optical scanners don't have more problems, because there is a computer element to it, but they seem to do okay. I mean, I guess they've done a lot, since they first came out in 1980. But yeah, so who knows? But yeah, I mean, just hooking up a printer and having it print out, and then just dropping it, the person inspects it and looks at it and dropping it into a box is not a problem. But IEEE, in their November Spectrum magazine, IEEE Spectrum, they actually talked about one solution where you could actually have anonymity and look at your vote on the net. And what it was is they talked about what you would do is you would have two encryption vendors. And what you would do is you would have two keys to go look at your vote and say, yeah, I did indeed vote that way, or you could look on the net later. So that was one solution they talked about. But there is a problem. You've got to come up with motivations so that the two vendors do not cooperate, because if the two vendors cooperate with each other, then you wouldn't have anonymity anymore. They could work with each other and get identities of people. So, but that was a solution they came up with, and if you have really strong motivations for them not to work with each other, then that would be a good way to go. All right. Any other questions here?
Yeah, I have a comment. First of all, I agree with you. 5 or 6 years ago, I worked for the EU in the electronic voting project. That is, the politicians and bureaucrats in the EU want us to vote in government voting electronically. And we who work with it pretty much proved that it is, as far as we know, impossible to build a secure electronic voting system. And the current paper voting systems we have in Europe, most of them are very good and very secure, and none of the suggested algorithms even for electronic voting comes even close to the safety we have with our current paper systems. So my personal take of this, and also most of those who work with it, because we left the project because we thought it was silly, all of us, is if the government tries to force you to vote electronically, don't do it. Stick to paper. It's much safer.
Yeah, in the United States, you can do absentee ballot, and that's one way that you can to go. But the problem is, like what happened in this last election in Florida, and apparently they did correct it, but they lost in Broward County, which is a predominantly Democratic county. They lost a whole bunch of absentee ballots, and they blamed the Postal Service for it. The Postal Service is like, hey, but they lost a whole bunch of those. So paper, sometimes you might think you're coming up with something, by doing paper, but sometimes they even find ways to play with that. So there's just no telling there. Anyway, so that's about it. Thank you so much.
I have another question, just a technical one over here. If I understood you correctly, the ballots that get in counted, they go from the Dball machine and they go to an administrative unit somewhere else, and then they go in a centralized counting unit from Dball. Is that correct? They get counted all the way from Dball. All votes.
Right, yeah, there's a
processed
central...
by Dball from the company there.
Right, exactly, which there's a vulnerability, just in...
Yeah, I was just wondering how that worked, so
Yeah.
not much of a question, but...
Yeah, no, like I said, it's been sent unencrypted. They've since fixed that kind of thing. I definitely have to call it right now because I'm really out of time, but I will be available for any more questions afterwards, so we'll talk some more right after. But thank you so much. You've been a wonderful audience. Thank you.